Hey, fifth graders, welcome back. Let's keep going on our lessons from the Earth and Sun unit. Last time we started learning about the sun by observing our shadows here on Earth. And I gave you a few activities to do at home. There were a lot of clouds last week, which makes it hard to study your shadows, but I did receive several photos of sun trackers and shadow outlines. And if you haven't done it yet, keep an eye out for the sun and get out there when you get the chance. We spent all that time talking about where the sun is going in the sky. But at the end, I asked you to think about what is actually happening. Here's our focus questions. What causes day and night? What causes the seasons? If you have some paper, pause this and write that down. Let's use a model to make sense of this. I'll have this orange represent the sun. All of the models we're using are not to scale. That means the sizes and distances are not right, but we're focusing on the orientation or position. Here we have the Earth's point of view. We see the sun rising in the east, traveling across the sky, and setting in the west. And then it comes back around and does it again. So you would think that the sun is going around the Earth, right? Don't feel bad if this is what you thought. It really does feel like we're sitting still, and it really looks like the sun goes up over there and travels all day and goes down over there. And for a long time, that's what lots of people thought was happening. They thought the Earth stood still, and the sun went around us. But then people like Nicholas Copernicus were like, wait a second, what if the sun isn't moving? What if we are moving? Let's try it again with the sun sitting still, but the Earth spinning around. They both created the same effect. Try it out. Find something on your wall to be the sun. Start spinning around slowly, looking straight ahead. It helps to have one eye closed. See if you can make the sun rise and fall. Oh, I'm a little dizzy from all that spinning. Hey, where'd the sun go?
Want some orange?
You're eating the sun?
Mm.
Well, I hope it tastes good. So, Copernicus was right. When you wake up in the morning, you're not in the same place you were when you went to bed. The Earth is moving. First of all, it's spinning or rotating on its axis, which is an imaginary line that runs from the North Pole to the South Pole. That's what you just did. Since you saw the sun appear once every rotation, can you guess how long it takes for the Earth to rotate all the way around? If you guessed 1 day, you're right. The Earth rotates on its axis every 24 hours. Let's bring back Mini Mr. Johnson to try this out.
Hey, fifth graders.
I'll use a lamp for the sun this time. Which way should I rotate it? He's facing east, and I know the sun rises in the east, so I'm going to rotate the Earth in that direction. If you're looking down at the North Pole, that's counterclockwise. He's in the daytime, and now the sun is setting, and now it's night, and he's coming around to the sunrise, and he's in the day again. Oh, that's gotta hurt. Notice how the sun rises at different times all the way around the world. That's why when you call your uncle in New York, it's 3 hours later there. Or when I call my sister in Australia, it's 17 hours later there. Try that activity again when you're spinning around. This time, make sure you're rotating counterclockwise. It might help to put the cardinal directions on your shirt so you can make sure to turn towards the east. Now try to stop at sunrise, noon, sunset, and midnight. So I think we've answered our first question, what causes day and night? Day and night are caused by the rotation of the Earth on its axis. Okay, next question. What causes the seasons? Remember when I said that you never really wake up in the same spot because the Earth is rotating? Well, that's not all. We're also revolving around the sun in a big loop. This loop is called an orbit, and it takes 1 whole year to complete. That means if your birthday is here on June 1st, it will take 365 days for Earth to return to this point in its revolution around the sun. That's all the days between your birthdays. But that still doesn't explain the seasons. Have you ever wondered why globes are tilted like this? It's not just so that they'll look cool. In Paris, they tilt their hats to look cool. But the Earth is actually tilted 23.5 degrees in relation to the sun. That means if you drew a straight line from the sun to the Earth, the axis line is not perpendicular. You might think a little tilt wouldn't be a big deal, but if you like snow days and hot summers, then it's a huge deal. That's because the tilt is what causes the seasons. Let's make another model to help our understanding. I'm going to use a marshmallow for the Earth with a toothpick through it to show the axis. You can do this too, plus it's a great reason to pull out some marshmallows. And I'll use an onion for the sun so that my assistant won't eat it this time. As the Earth makes its orbit around the sun, the tilt does not rotate. It keeps pointing in the same direction. So when the Earth is over here, the top half or northern hemisphere is leaning towards the sun. It's getting more direct sunlight. There's more sun, more heat, and it's summer. The day when we're tilted the most towards the sun is called the June solstice, and it's the day we have the most hours of daylight. The opposite is happening in the southern hemisphere. It's leaning away from the sun, and it's winter. When it gets over here 6 months later, the northern hemisphere is leaning away from the sun. It's the December solstice. The sunlight is not as direct, and it's winter. In the south, the light is more direct, and it's summer. Then 6 months later, we're back again. Here's another activity you can do at home. This one will help you understand why direct sunlight matters. All you need is a flashlight and paper and something to write with. Shine the flashlight directly at the paper and circle the outline of the light. Then point the flashlight at the same spot from the same height, but at an angle. Circle the new outline of light. The same amount of light energy was hitting these two spots, but when the light was at an angle, the energy was spread out over a much bigger area. You can see I used a graph paper for this, and when the light was direct, it was lighting up about 120 squares. But when it was indirect, it was lighting up almost 500 squares. So this represents in the summer, more direct light. You're feeling more of that heat. But in the winter, it's still light out, but that heat is spread out because of the indirect light. I think we can answer our second focus question now. The seasons are caused by the tilt of the Earth in relation to the sun. The angle of our sunlight makes a big difference. Let's think a little bit more about direct and indirect light. The two places on Earth that get the least amount of direct light are the Arctic in the north and the Antarctic in the south. And that's why these two places are the coldest spots on Earth. I know because I once had the chance to work for 4 months at McMurdo Station in Antarctica. The sun was always lower in the sky, so we always had long shadows. But that's not all. Since we were there in the summer, the sun never even set. It was sunny all day and all night. This is because when the polar regions are tilted towards the sun in the summer, they never even get on the dark half of the Earth. But since the light is at such an angle, the temperatures stay cold. Luckily, I wasn't there in the winter because it would have been dark the whole time. The place where the northern hemisphere and the southern hemisphere meet is the equator. It's an imaginary line that runs around the center of the Earth. And no matter where the Earth is in its orbit, the equator is getting mostly direct light from the sun. Because of this, people living near the equator don't experience the changing of the seasons like we do. When the Earth is halfway between the solstices, it's called an equinox. There's one in September when we have fall, and one in March when we have spring. On an equinox, there are equal hours of light and dark on the whole Earth, even Antarctica. Watch this video I made a few years ago when I was at the equator in the Galapagos Islands on a teacher fellowship with National Geographic. Okay, I'm here near the equator in the Galapagos Islands on the fall equinox. And fall equinox, basically, because of the tilt of the Earth, this is when the sun is directly 90-degree angle to the equator. And so when you're standing near the equator on the fall equinox at noon, you're going to have the very smallest shadow you've ever seen. And so we'll back up here and take a look at this. Not very common for those of us in the Northwest. I don't think we ever see the sun that high. Anyway. There's one more thing for this lesson. We've been talking so much about how the sun affects us here on Earth, but some of you had questions about the sun itself. Kai asked, why is the sun so hot? Even though the sun is 93 million miles away, it can burn our skin and blind our eyes here on Earth if we're not careful. That's because there is a lot of heat and light energy being released by the sun. Luckily, we're not closer to it because the surface temperature is around 5,500 degrees Celsius, and the temperature at the center of the sun is 15 million degrees Celsius. That center part is called the core. It's where all of the heat and light energy is created, as hydrogen is constantly changing into helium in thermonuclear reactions. The sun isn't just hot, it's huge. This illustration compares the size of Earth to the sun. You could line up more than 100 Earths along the face of it, and more than 1 million Earths could fit inside. We'll talk more about the sun when we talk about the solar system. Next time we'll be talking about the moon, so start thinking about that. If you did any of the activities that I shared, take a picture and send it in. I'll put it in the next video. And also send me your moon questions. See you next time. I'm going to add in just a few fun things to think about. How long does one date last? We know one day is 24 hours, but how long is it a certain date on Earth? And the surprising answer is about 48 hours. If your birthday is June 1st, your birthday actually starts at 7 a.m. the day before on May 31st out in the Pacific Ocean at the International Date Line. And it starts moving around, your birthday gets going as all the way around the globe, it gets to you and you enjoy your birthday, and then your birth date doesn't actually end until 7 a.m. the day after your birthday on June 2nd. These times are for our West Coast time zone. But anyway, don't forget this. Next time it's your birthday, take advantage. Start celebrating the day before. Have a good birthday breakfast the day after your birthday, because your birthday lasts for 48 hours on this planet. What really makes night? I think we figured out that it's not because the sun went down. We're actually facing away from the sun, which means that we are in a giant shadow when it's nighttime. We're in Earth's shadow. So think about that tonight when it gets dark outside. You're just in a big shadow. You know how we said that we're always moving even though it feels like we're sitting still? I always wonder how fast we're actually moving. Well, first of all, we are rotating on the axis where we live around 750 miles an hour to get all the way around in 24 hours. It's faster at the equator. And then we're also, as we're orbiting about 67,000 miles per hour to make it all the way around the sun in a year. And then our solar system is spinning in our galaxy, and our galaxy is moving also. I don't even know how fast we're really going. Maybe that's something one of you could figure out, but I think that's going to take a lot of calculations. And of course, sometimes we're rotating back and revolving forward, so that speed is changing. But it's kind of fun to think about that we're moving all the time. Marshmallows.